Alrighty, so my name is Jayden Rumfellow, and this is the bomb calorimeter experiment. So first, our main objective of this experiment was to become familiar with the physical principles, procedures, and the analysis techniques associated with the oxygen bomb calorimeter. So some theory behind that: the part oxygen bomb calorimeter measures the heat of combustion for the solid and liquid samples. The bomb ignites, and the heat is transferred by conduction. And the definitions on the right side say that the heat of combustion is the number of heat units liberated by a unit mass of a substance when combined with oxygen in an enclosure of constant volume, and the conduction is the heat that is transferred from the internal surface to the surrounding water environment. And then also on the left side, I have the high versus low heating value of a fuel. So the high heating value is equal to the total amount of heat released by a fuel sample that returns to the pre-combustion state, and then the low heating value is equal to the high heating value minus the sample's heat of vaporization. And then here is just the first law of thermodynamics, and it says that the heat of combustion is equal to the thermal capacitance times the change in temperature, and then you can also use the thermal capacitance is equal to the heat of combustion divided by the temperature rise. So right here we have the procedural setup that we use for the experiment. Number 1 is the igniter, 2 is the stainless steel bomb housing, 3 is where the laptop with the VDAC view was connected, and 4 is the analog digital converter, 5 was the water bucket, and 6 was the thermocouple, and 7 was the stir motor. And this is the blown up view of the bomb. So at the top we have the electrode terminals, then we have the pressure relief valve, the lid locking ring, the ignition wire, we have the bomb housing, the crucible, the 2 electrodes, and then the inlet check valve. Here is some of the raw data that we had got from the experiment, and the temperature was recorded in degrees Celsius. The data was recorded every second, and this is kind of hard to analyze in the tabulated form. So next I have the plots of the data. On the left side we have the benzoic acid temperature versus water, and on the right side I have the Skittle gummy water temperature versus time. And then some notes here: it was easier to analyze a trend here. The X and Y axis vary on each graph, and the benzoic acid temperature jumps at about 210 seconds, while the Skittle gummy temperature jumps at about 50 seconds. And then right here I calculated the heat combustion of the ignition wire. So for the benzoic acid, the heat of combustion of the ignition wire was 23 cals minus 9.5 cals, which equaled 13.5 cals. They converted to 56.48 joules, and it gave you 0.6565 kilojoules. And then right here on the Skittle gummy, the heat of combustion for the ignition wire was 23 cals minus 17 cals, which gave us 6 cals, converted to 25.10 joules, and one more conversion gave us 0.0251 kilojoules. And then here are some calculations. So this is where objective 2 came into play. It said to determine the thermal capacitance of the calorimeter. So I have the values in the table on the left side, and that shows that the minimum temperature calculated was 22.701 degrees Celsius, the maximum was 25.186, and the change in temperature was 2.485 degrees Celsius. So our mass of the acid was 1.02 grams, and then that gave us a thermal capacitance of our known thermal capacitance was 26.38 times the grams, which is 1.02 grams, which equaled 26.9 kilojoules. The Q of the wire was from the slide previously, which was equal to 0.0251 kilojoules, and the change in temperature was the 2.485. And so we solved for the thermal capacitance here of the calorimeter by putting the combustion of the acid plus the combustion of the wire and divided that by the change in temperature, and we got that to come out as 10.85 kilojoules per degree Celsius. And then here, objective 3 was to determine the gross heat of the combustion of the samples provided. So we had a known thermal capacitance of 10.85 kilojoules per degree Celsius, which was equal. And then the heat combustion of the wire was 0.0565, and the change in temperature here was 0.752. And so to solve for the heat of combustion for the Skittle gummy, we did the thermal capacitance times the change in temperature minus the combustion of the wire, and that gave us a value of 8.1 kilojoules per gram. So here is like the quality of the results. So online, the Skittle gummy nutrition fact shows that there are 90 calories per 28 grams. So I calculated this right here with those facts, and I got 13.4 kilojoules per grams. So based on our data and the data from the actual Skittle gummy pack, that we came up with a relative error of 39.6, which is kind of high. I think that could maybe be caused because we didn't have enough oxygen in our thing to get us to 30 atmospheric pressure. We were only able to get to about 20. And then here is the data comparison. So the experimental heat of combustion for the benzoic acid was 26.83. The known was 26.83 also. The change in temp was 2.485 degrees Celsius. The time to reach the max temperature was 386 seconds. And a fuel with a similar known combustion is coal, which it comes up at about 27. And then for the Skittle gummy, we have the experimental heat of combustion to be 8.1, the known heat of combustion to be 13.4, the change in temp to be 0.752. The time to reach the max temperature was 261 seconds, and a similar fuel with that known is dry wood at 14.8. And then here are my references.